Welcome to this first lecture about solar energy, a huge source of energy on Earth. Today we will look at heating applications. And we will also see that solar heat can be used to produce cold and electricity as well. The use of solar photovoltaics for electricity production will be handled in another lecture. This is our last lecture on heating systems. You probably all know such pictures with the energy balance on Earth. What is important is the quantity of energy arriving on Earth's surface, which amounts 163 watt per square meter on average. If we multiply it by the number of hours in a year, 8760, we get 1430 kilowatt hour per square meter annually. As the surface of Earth is 510 billion square meter, the total energy available on Earth is 729,000 petawatt-hour. The total annual energy used by humans is evaluated to 160 petawatt-hour, which is 4,500 times smaller. So there is plenty of energy around. Of course, if we look at its global distribution, it is clear that there are large differences all over the world. Northern countries receiving 0.8 to 1 megawatt-hour per square meter annually, and southern countries 1.8 to 2.7. Those are, however, annual averages, hiding the reality that this energy is not always there. So, here, as an example, the daily variation of solar radiation in Mumbai for a typical week, and on the right, the same for the Netherlands, above for a summer week and below for a winter week. As you see, we don't have too much in winter here. The intermittency of solar radiation is the largest limitation we have to deal with when developing solar systems. In many countries, next to dealing with the daily intermittency, we also have to deal with the seasonal one, and of course the month with less radiation corresponds to the coldest ones, where space heating is needed. As for the winter, it is very much the question how far we can go with solar energy. We would need storage capacity to bridge day and night, and probably seasonal storage between summer and winter. We will address this a bit later. The curves you see here are for an horizontal plane. Of course, it would be better to place a collector on an inclined plane exactly perpendicular to the solar radiation. This is the reason why collectors are often placed with a certain inclination depending on the location. However, most collectors do not track the sun, so for a large part of the day they are not perpendicular to the radiation. Modern collectors are less sensitive to the exact direction and can even be placed almost horizontally. It is good to inform, though, what is ideal for a specific collector at a specific location. First, a few words about the passive use of solar energy in buildings. In the MOOC Energy Demand in Buildings, you have learned about the impact of solar radiation on the energy balance of a building and how you can play with it by using blinds and overhangs and choosing the right type of window with the right solar factor G, the right orientation and the right type of construction, light or heavy. We described how solar radiation does not directly heat the air, but only indirectly by heating the walls, which then give their heat back to room air by convective flows. The more mass in the construction, the slower the process. The so-called trombe wall makes use of this phenomenon by absorbing solar heat during the day and releasing it in the evening and night. This works best to cover day-night differences in heating demand. More active versions of the trombe wall could include phase-change materials like paraffins, which would smelt when submitted to solar radiation, storing this way a lot of latent heat to release it at night by solidifying again when there is no radiation. Modeling the effect of walls and phase-change materials is beyond the scope of the course, especially because modeling this time delays is complex and will be addressed in an advanced modeling course. A few additional words about solar radiation, as it is important for the performances of collectors and cells. When the sun is shining, we call its radiation direct radiation. When it is not shining, we call it diffuse radiation. Generally, diffuse radiation is less than a direct radiation. In this course, we will consider the global radiation, which is the sum of both. When the sky is overcast, there is only diffuse radiation. When the sun is shining, both diffuse and direct radiation are present. These radiations are generally measured by meteorological institutes on an horizontal surface or on a surface perpendicular to the sun, the so-called normal radiation. Solar collectors is the name we use when we collect only heat and not electricity. The principle of a solar collector is quite simple. You can even make one yourself quite easily, although its performances may be quite low then. It's just a water pipe, by preference black, to absorb as much as possible solar radiation. The water comes cold in at TW1 and is heated directly by the absorbed solar radiation to TW2. To limit the heat losses, it is quite important to insulate well the backside of the collector and to place a glass cover above the pipe, preferably glass with a high transmission factor in the light spectrum. The glass is not transparent to infrared radiation and the heat losses in the pipe are in the infrared spectrum. So the glass captures this energy. That's the same principle as in greenhouses. We can easily write an energy balance on this collector. First, the water in the pipe will be heated by the sun from TW1 to TW2. If we have a flow rate m, the energy taken by the water will be mCp times TW2 minus TW1. This energy is provided by the solar radiation Q-Sol falling on the collector. From this incoming radiation, only the fraction tau that is transmitted through the glass and absorbed, that is alpha, through the pipe, is transmitted to the water. For the ease, we will use the coefficient beta, which is tau times alpha. There is also energy lost by transmission and radiation losses, just like the transmission through walls and windows in a building, like in the coarse energy demand in buildings. So finally, we can write that the heat absorbed by the water is the energy received from the sun minus the losses. If we know the solar radiation and the losses, we can easily calculate how warm the water will be at the end of the collector by using the first equation. But how to determine the losses? Q-loss is mainly proportional to the temperature difference between the collector Tm and the outdoor temperature To, where C1 is the convective heat transfer coefficient in watt per square meter Kelvin. To account on a simple way for the radiation losses, an additional term with the square of the temperature difference is used. But what is this Tm temperature? Well, that is the average between the inlet and outlet water temperature. And also a remark on the surface A. It is the surface of the glass plate of the collector, so in Q-loss the coefficients C1 and C2 account for the fact that there are also losses on the back and sides. Why am I telling all this? Well, that is because producers either give the C1, C2 and beta values of their collectors, so you need to know how to use it to estimate the power, energy and hot water temperature delivered by the collector. One small problem with this is the Tm temperature that you don't know and which appears in a square in the last equation. For rough estimation, you can, however, assume C2 to be 0, which will simplify greatly the calculations. And otherwise, you have to write a small piece of code to find the right solution. Sometimes producers don't give beta C1 and C2, but directly the efficiency of the collector, which follows from the previous slide. And you can directly write Q water is ET times A times Q sol. You see on the left a typical efficiency curve given against Tm minus To. To is the outdoor temperature, Tm is the average temperature on the collector. Let's look how to cope with that on an example. Imagine a solar collector of 1.6 square meter. The solar radiation is 800 watt per square meter. The incoming water temperature is 12 degrees Celsius. The outdoor temperature is 10 degrees. And the water flow rate is 0.015 kg per second. The specific heat of water, Cp, is as usual 4180 joule per kilogram Kelvin. What is the heating power Q water, and how warm will the water be at the pipe outlet? The first thing we come across is that we don't know what Tm is, but we need it to estimate the efficiency. The simplest way to cope with that is to linearize the curve between values of delta T that seem realistic. In this example, I thought that the temperature difference between Tm and the outdoor temperature will probably not exceed 50 degrees, so I linearized the curve between 0 and 50. See the red line. Such a line has an equation of the type Et is A plus B delta T. In our case, the value of delta T is 0. At 0 is 0.7, so A is 0.7. As for B, the efficiency decreases by 0.1 for a delta T of 50, so B is 0.1 divided by 50 equals minus 0.002. This was step 1. And of course, we know that Tm is the average of Tw2 and Tw1, so we can rewrite the efficiency like on the slide. In step 2, we replace Et by its value in the first equation, and we remember that Q water is mCp delta T. This is a quite simple equation with which you can easily calculate Tw2 and then Q water. I came here to 25.9 degrees for Tw2 and a heating capacity of 872 watt. To deal with the intermittency of solar radiation, we can either wait for the sun to shine or use a storage tank and fill it with hot water when the sun shines. I'm talking now about hot tap water. In a system with a tank, cold water is fed underneath and a heat exchanger with the water coming from the collector heats the water. Warm water rises so the outlet pipe to the taps is located above. Real simple and effective. Care has to be taken that, especially in larger tanks, the water can be heated once a week to 65 degrees to kill the Legionella bacteria. If that is not possible with the solar collector, an additional electrical resistance can be used. In colder countries, such a solar boiler is even always combined with additional heating by either a combustion or an electrical boiler. In the Netherlands, for instance, solar boilers can be installed around 4 square meters per house, and they manage to produce approximately half of the needed hot tap water. The liquid circulating in the collector is then not water, but generally an antifreeze mix of water and glycol, and the tank will always be placed indoors. In warm countries, it will look more like that. Additional heating is not often necessary, and the tank may be much smaller, as there is much more incoming solar radiation. There are many ways to improve the efficiency of the simple solar collectors we described earlier in this presentation. Vacuum collectors, for instance, have much less heat losses and therefore a higher efficiency. In a vacuum collector, the water pipe circulates in a vacuum pipe containing an absorber plate, and they are connected in parallel to the water pipe. Concentrating collectors concentrate the solar radiation on the water pipe. It collects this way radiation that would otherwise fall at another place and can concentrate the radiation 30 to 100 times. Very high powers can be achieved this way. In fact, the power may be so large that temperatures far above 100 degrees can be achieved, by which steam is produced and drives a steam turbine. So, electricity can be made from solar heat. There are also sun tracking collectors following the movement of the sun. In this picture above, the heat collected is above 400 degrees and is used to make electricity using a so-called Stirling engine, which is a kind of combustion engine without combustion. Last, but certainly not least, the PVT collector deserves some attention. The PVT collector is a combination of PV cells, which are the subject of another lecture, and a solar collector. The water in the pipes of the collector reuses the heat wasted by the PV cells. It is therefore a kind of cogeneration of heat and power. We have focused on solar collectors for hot tap water and just have seen that solar heat can also be used to produce electricity if a high enough temperature is achieved. But there are many other relevant applications. The warm water from the solar collector can be used as heat source for heat pumps. This increases the COP of the heat pump a lot, as the collector water has a quite high temperature. It can also be used to regenerate, which means to bring the ground at the right temperature when a ground source heat pump is used, or to regenerate the warm well of an aquifer thermal storage when there is an imbalance, and that is done quite often. It can also be used as source for low temperature heating networks. This would work exactly the same as with low temperature geothermal systems. And finally, instead of circulating water in the collector pipes, air can be circulated and heated this way. So you see that there are plenty of useful applications. As last example, solar collectors can be used to deliver heat to the absorber of absorption chillers. These chillers generally use the mixture water lithium bromide or a mixture of ammonia and water. In conventional absorption chillers, the desorber temperature is above 80, but the new generation can also cope with 65 degrees Celsius, by which the use of solar heat becomes very attractive. The EER of such a solar absorption chiller is around 0.6 to 0.8 and may be above 1 if more complex cyclones are used. To summarize this lecture, you have discovered the huge potential of solar collectors for diverse applications. You also have basic knowledge about the efficiency of such collectors and how to cope with producers' data sheets. You are aware of the fact that the sun does not always shine and what that means for the design of such collectors, in particular the necessity for heat storage, especially in colder countries. Goodbye and thank you for your attention.